A mass weighing 56 pounds stretches a spring 8 inches. The mass is in a medium that exerts a viscous resistance of A pounds when the mass has a velocity of 6 feet per second. The system will be overdamped if A is greater than how many pounds? So if we assume there are no other outside forces acting on the system, we could model the situation using the linear second-order homogeneous differential equation given here, where m is the mass, gamma is the damping coefficient, and k is a spring constant. To solve this system, we would use a characteristic equation, and based upon the type of solutions to the characteristic equation, we can determine the type of damping. If gamma squared minus 4mk equals 0, the system is critically damped. If gamma squared minus 4mk is greater than 0, the system is overdamped, which is what we want. And if gamma squared minus 4mk is less than 0, the system is underdamped. We should recognize this would be the discriminant of the corresponding characteristic equation. So by determining the nature of the roots of the characteristic equation, we can determine the type of damping. Let's begin by listing all of the given information. Notice how we're told the weight W is equal to 56 pounds. The spring is stretched 8 inches, so L equals 8 inches. But we need this to be in feet because notice how the velocity is in feet per second. 8 inches equals 2/3 of a foot. And we're told the viscous resistance is A pounds when the mass has a velocity of 6 feet per second, which means the damping force, F sub D, is equal to A pounds when the velocity, because the displacement function is u of t, would be u prime of t equals 6 feet per second. So now we'll find the mass, damping coefficient, and spring constant, and then we'll set up this inequality here and solve for A. So the mass is equal to the weight divided by the acceleration due to gravity, or W divided by G, which would be 56 pounds divided by 32 feet per second squared, which simplifies to 7/4. This would be slugs. If we want 1.75 slugs. Next, we'll find the damping coefficient using this formula here. The damping force is equal to the opposite of the damping coefficient times the velocity. But because the damping force is always in the opposite direction of the velocity, we can actually ignore this negative sign and say that the damping coefficient is equal to the damping force divided by the velocity. So we would have A pounds divided by the velocity, which is 6 feet per second. So we'd have A divided by 6. We can write this as pound seconds per foot, or if we want, we can write this as pounds per foot per second. And then finally, the spring constant K is equal to W divided by L, which in this case would be 56 pounds divided by 2/3 of a foot, which would be 56 times 3/2, which equals 84, and the units would be pounds per foot. Now that we know m, gamma, and k, we can set up the inequality for an overdamped system and then solve for A. Let's do this on the next slide. Again, because we want the system to be overdamped, we'd have the inequality gamma squared, which would be the square of A divided by 6 minus 4 times m times k, so times 7/4 times 84 greater than 0. So the square of A over 6 would be A squared divided by 36 minus, notice here the 4 is simplified to 1. 7 times 84 is equal to 588. So we have minus 588 greater than 0. Adding 588 to both sides, we have A squared divided by 36 greater than 588. Multiplying both sides by 36, we have A squared greater than 21,168. Remember, A is going to be force in pounds, so now we would take the principal square root of both sides of the inequality. So we'd have A is greater than, this simplifies to 84 square root 3, which is approximately 145.4923. So going back to our first slide, we'll use the approximate value of 145.4923, and this would be pounds. So if the viscous resistance is more than 145.4923 pounds when the mass has a velocity of 6 feet per second, then the system will be overdamped. Now before we go, let's quickly review these three types of damped systems. A critically damped system returns to equilibrium as quickly as possible without oscillating. An overdamped system, which is our system, returns to equilibrium without oscillating. But notice how it doesn't say as quickly as possible. And then 3, an underdamped system oscillates with the amplitude gradually decreasing to 0. And it's also worth mentioning that an undamped system oscillates at its natural resonant frequency. I hope you found this helpful.